So let me start by thanking the organizers for the invitation. It's really nice to be here today. It's been a pleasure over the last 10 years or so to become a member of the Brazilian mathematical community. And I want to talk today about some of the results I obtained with the different colleagues from different Brazilian universities. And the talk is going to be divided into two parts. So on the first part, I'm going to talk about qualitative results concerning the regularity for singular and degenerate parabolic equations. And I will try to explain in a very sketchy way the so-called method of intrinsic scaling introduced by Devido in the 1980s. And then on the second part of the talk, I will consider quantitative results. So in which we are not so much concerned with proving that the solutions of certain PDEs have, for example, that they are Holder continuous, but more on showing what is exactly the Holder exponent, for example, or trying to derive a precise modulus of continuity for these equations, for the solutions of these equations. So to try to understand the method of intrinsic scaling, let me start with the Georgi's solution of Hilbert's 19th problem and the proof that he did that elliptic linear equations in divergence form with coefficients that are only measurable and bounded are in fact Holder continuous. So the method of de Giorgi is an iteration method. So based on this idea that if you want to prove the continuity at a point, what you have to do is to build a sequence, say, of balls centered at the point, and measure the oscillation of the solution in these balls and show that as the balls shrink to the point, the oscillation goes to zero. And if you can measure the way this oscillation goes to zero, you can derive a modulus of continuity, okay? So I made this picture here. This is more adapted for the parabolic case, but this is the idea. So you have a sequence of shrinking balls or cylinders or boxes, whatever you want to call it. And then you measure the oscillations in this sequence and you show that as the balls, these boxes shrink to the point, the oscillation goes to zero. Now, this is an iterative method and everything is based on the so-called Cacciopoli estimates on level sets. So for the type of equation that de Giorgi considered, so a prototype is this. So you have a coefficient matrix A. So these Aij's are, as I said, only assumed to be bounded. And you have this linear equation in divergence form. You can easily derive these Cacciopoli estimates on level sets. So K is some positive number. U minus K plus is the positive part of the function. So this is U minus K if U is above K, and this is zero if U is less or equal than K. And you see that these estimates, they are a sort of reverse Poincaré inequalities. Because here, I mean, forget this cutoff function zeta. What you are doing is that you are controlling the L2 norm of the gradient of these functions U minus K plus with the L2 norm of the function. So Poincaré is the other way around. You control the L2 norm of the function using the L2 norm of the gradient. And this is what I call the building blocks of de Giorgi's theory, because everything follows from this, right? Once you obtain these estimates, I mean, you can, for example, forget the equation. I mean, it doesn't matter if this U is a solution of a PDE, if it's a minimizer of a functional, if it's just a function that belongs to the class of functions that satisfy these inequalities for every K positive. So these are the basic estimates in the elliptic case of DiGiorgi. And what happens if instead of a linear equation like this, we have, for example, the P-Laplace equation, which is a nonlinear equation. More than being nonlinear, the principal part grows nonlinearly with the gradient. And you see that if you try to derive the same type of Kac-Shapely estimates, the only difference is that you replace the power 2 here, these 2's that appear in the case of the linear equation, by p's, right? So if p is less than 2, this equation is singular because this modulus of ellipticity will go to infinity at the points where the gradient vanishes. If p is greater than 2, then the equation is called degenerate because this vanishes. This modulus of ellipticity vanishes at points where the gradient is 0. So the only difference is that you replace 2 by p, and in fact, that's what made possible the extension of the results of DiGiorgi to the, say, elliptic P-Laplace equation by Ladizhenskaya and Uraltseva in the 1960s. So this was a pure adaptation of the method because, in fact, I mean, it's like going from the Hilbertian case to the case of a Banach space. So everything works fine. You, instead of working in H1, you work in W1P, and you still have the Sobolev embeddings that you can use to, once you have the Kac-Shapely estimates, to make the method work. Now, when you go from the elliptic to the parabolic, what happens is this. So going to the first example and now adding this time derivative term and writing the Kac-Shapely estimates, the corresponding Kac-Shapely estimates for this case, what happens is that, I mean, these are the terms coming from the elliptic part, so the principal part of the equation, the two that we are now familiar with, and from the, say, the parabolic term, the time derivative of u, we obtain 3 additional terms, these ones here. And again, you see that, so basically you derive these estimates by testing the equation with u minus k plus zeta square. So you see that from the time derivative, you get these terms with power 2. And if you look at this estimate, you see that you have power 2 everywhere. So the estimate becomes, remains homogeneous when you go from the elliptic to the parabolic. And because of this homogeneity, the same method was extended to the parabolic case for an equation of this type, still by the Russian school in the late 1960s. So everything worked fine because, again, you have the right powers, everything is 2, you have a nice Sobolev parabolic Sobolev embedding, and the method can be reproduced in this case. However, if instead of a linear principal part, you have the P Laplacian in the principal part, so if you have the parabolic P Laplacian, dtu minus P Laplacian of u equals 0, what happens when you write the Kac-Shapely estimates is that, of course, from the time derivative term, you cannot escape having the power 2 in here, because, I mean, this is the typical scaling that comes from the time derivative term. But for the principal part, for the P Laplacian, you have, of course, the power p. So this is exactly what appears, the 2 terms on the estimate that appear for the case of the elliptic P Laplacian. So now you have a problem because you have different powers. You have power 2 and you have power p, and the estimates are no longer homogeneous. And this is what prevented the method to be adapted for this case. And we had to wait 20 years. Only in the mid-1980s, it was possible to understand what happens in this case. And the way to understand what happens is to try to recover the homogeneity in these estimates. Because if we have power p everywhere, so if we can somehow, by some magical trick, change these 2's into p's, everything would work fine. So, but how are we're going to do that? So to get a hint on what to do, let's look at a different equation where instead of having here the time derivative of u, we have the time derivative of u to the power p minus 1. So when you multiply by u, you get, of course, power p in the terms coming from the time derivative, and you get homogeneous estimates. So it seems that for this PDE, which is called Schrödinger's equation, everything would work just fine. So let's compare this PDE with the P-Laplace equation that we had before. So I wrote here in this line the P-Laplace equation in a different form to understand the difference between these two. Look, here, if you take the derivative of this term, what you're going to get is the exponent p minus 1, then you get u to the p minus 2, and then you get the time derivative of u. So this u to the 2 minus p cancels with this u to the p minus 2. And you choose the constant such that this constant to the 2 minus p cancels this p minus 1. Okay? So when you do this derivative, you are only left with exactly the time derivative of u, which is the P-Laplace equation. So that's why this here is, in fact, this equation is the P-Laplace equation. This one here. And so if you compare with the previous one, this is Schrödinger's equation. And the P-Laplace equation is this multiplied by this factor. So what I want to say with this is that if we can get rid of this factor, we obtain an homogeneous equation. So if we have the P-Laplace equation, if we somehow manage to get rid of this, we get an homogeneous equation, we get homogeneous Kac-Szopoli estimates, and everything should work when proving the Hölder continuity of solutions. So how are we going to do this in a rigorous way? Of course, like not just simply divide by this and discard this factor. So the idea of intrinsic scaling is this. When you do this analysis in this sequence of boxes, so here this direction represents space and this represents time. So these are typical parabolic cylinders. The standard scaling would be to consider a radius r in space and the radius r to the p in time, right? For example, for the heat equation, the standard scaling is r squared, okay? So typically you would think that this reduction of the oscillation analysis should be made in boxes that reflect this, say, natural homogeneity of the equation, and you should consider boxes that scale like r in space and r to the p in time. But if you do the analysis in these boxes, what you get are estimates, as we've seen before, that are not homogeneous, because you're going to get power 2 from the terms coming from the time derivative and power p from the terms coming from the principal part, the P-Laplacian. So the idea of intrinsic scaling is in doing this oscillation reduction, not in the standard parabolic cylinders, but in cylinders that are scaled in the right way to somehow accommodate the degeneracy of the equation. So the idea is that instead of doing the analysis in boxes like this, we stretch these boxes and do the analysis in boxes that are longer in the time direction, right, by multiplying r to the p by a certain factor a0. Now, what is this factor? So this factor is going to be defined in the following way. So you start with a cylinder, it's this dotted cylinder that I have here, this larger one, okay, q r square r to the p, so r is small, so typically r square is larger than r to the p. You measure the oscillation of the function there, you call it omega, in this starting box, and then you divide this, you define this constant a0, this stretching constant, in the following way. So you divide the oscillation by an appropriate constant, depending only on the data, and you take this to the power 2 minus p. So I'm considering now only the case p greater than 2. Now you see two things. First, if p is 2, so if we have exactly the heat equation, then of course this is going to be 0, a0 is going to be 1, and we have exactly the standard parabolic cylinders q r square r, reflecting the normal, the natural homogeneity between space and time in the heat equation. And again, you see that this is a large number typically, because if p is greater than 2, so this is negative, this power, 2 minus p. And of course, this is a small number because the oscillation is typically a very small number divided by a constant. This is going to be a large constant. So this is a very small number. You take this to a power which is negative. This is going to be quite large, right? So you are in fact, by multiplying by this factor, you are in fact stretching the cylinder in the time direction. Now, if you compare this this scaling factor with the factor that you want to get rid of to get the homogeneous equation, you see that they are, of course, very similar, right? So here you have the solution divided by a constant to the power 2 minus p, and here you have the oscillation of a solution divided by a constant to the power 2 minus p. All right, so they are very similar. And you call this intrinsic scaling because you are scaling with a factor that depends on the oscillation of the solution, right? So it's intrinsic to the solution in this sense. Now, how do you recover the homogeneity in the Kac-Chopley estimates? By doing the analysis in these stretched cylinders. So the term where you have problems is this, right? You have power 2 there and you have power p, and you want to have power p throughout, right? So for example, take a constant, this k, to be the supremum of a solution in this original box minus the oscillation divided by a constant. So this is a constant that is typical in this analysis. So you see that u minus k plus, it's either 0, where if u is less or equal than k, or this is u minus k when it is not 0. So if k is this, you replace there, so u minus k is u minus mu plus omega divided by c, right? And since this is the supremum, u minus the supremum is of course less or equal than 0, so all this is less or equal than omega divided by c. So here you have your square, and you want to replace it by the p. So this is, of course, the square is, of course, equal to u minus k plus to the power 2 minus p multiplied by u minus k plus to the power p, right? I mean, these two cancel, and you just get the 2 there, right? Now, this you don't touch, okay? It remains here. But this guy, you see, I mean, if it's 0, then everything is 0. If this is not 0, this is less or equal than omega over c. So since the exponent is negative, this is going to be greater or equal than omega divided by c to the power 2 minus p. And this is precisely the a0 that we defined before, okay? So this is precisely the a0 that we defined before. And so I can replace the square there by the p, right? So this is going to be greater or equal, but that's fine because I mean, I want to, this is on the left-hand side. I want to, if I bound this from below, it's okay, right? The price that I have to pay is the appearance of this constant A0. Okay, so I replace the 2 with the P and I pay this price of having this scaling factor over there, right? Then what do? I just divide throughout the inequality by this A0. It disappears from here. It's going to appear here as 1 over A0. And then what I just have to do is to do a change in the time variable. And if I do a change in the time variable, what do? I rewrite these inequalities in the stretched cylinders, because now if I do a change in the time variable, I mean, this thing is going to be absorbed because it's going to cancel with the Jacobian of the transformation. And I rewrite the Kac-Shapoli estimates over these rescaled boxes, and the estimates become homogeneous. Okay. So in this way, we recover the homogeneity in the estimates, and we disclose the right Sobolev, parabolic Sobolev embedding, and we can carry on with the standard proof. So this is the idea, okay? If we write the estimates in boxes like this, then the estimates become homogeneous. So this is a very simple idea. So the difficulty in the analysis is somehow absorbed by the geometry in which you do this analysis. So, and you can say, I mean, to simplify, that the equation behaves like the heat equation in its own intrinsic geometry. And this is the essence of the method of intrinsic scaling. So you have to do this, reduction of the oscillation, not in the standard parabolic boxes, but in boxes that must be redefined, that must be scaled according to the nature of the degeneracy in the equation. So for each PDE, you have a certain type of boxes in which you can do the analysis in the right way. So this is a very robust method, but this method only gives you qualitative results. So it tells you, for example, that solutions of the parabolic P Laplacian are Holder continuous for a certain alpha, which is a very small number, but it's impossible to track in this analysis. So in the spirit of what Boyan was saying earlier, let's, on this second part of the talk, consider sharp results. So now we are not so much concerned about saying that the solutions are C alpha or C1 alpha, but more on trying to be precise about these exponents, saying exactly what is the alpha, saying exactly what's the modulus of continuity, and so on. And maybe I can move a little bit quickly now, because Boyan already explained these ideas of tangential analysis. So, I mean, again, these are based on iterative arguments. And the idea is that when you have an inhomogeneous equation, you can touch it by solutions of the homogeneous equation, which are typically more regular. And then you try to import this regularity corrected according to the intrinsic scaling of the PDE. And by doing this, we were able, with the different colleagues, mainly from Brazil, to obtain this type of sharp results that I want to tell you about. The first one is a collaboration with Eduardo Teixeira, who was at the time at UFC in Fortaleza, and he's now in Orlando, Florida. And we've shown that solutions of the parabolic P Laplace equation that were known to be C0 alpha since the 1980s, with the right-hand side with this integrability, so LQ in space and LR in time, solutions are precisely C0 alpha, and the alpha is this number that depends only on the P, the space dimension N, and the integrability exponents of the source F. Okay, so it's exactly this number, PQ minus N multiplied by R minus PQ divided by Q, P minus 1R minus P minus 2. Okay, few comments about this. Of course, we are making assumptions on the integrability of the source, so it has to be sufficiently integrable. So Q and R, they must be sufficiently large so that you can prove the Holder continuity, of course, and this is the typical assumption. So they have to be large enough so that this inequality is satisfied, but you don't want them to be too large, because, I mean, if they are too large, then you enter the C1 alpha regime, and it doesn't make any sense to look for the beta alpha in the C0 alpha regime, because then solutions will be Lipschitz, locally Lipschitz. So you also assume that they are not too large, so they cannot violate this other condition. And for those more familiar with elliptic problems, I mean, these two conditions in the elliptic case would be saying that the right-hand side is between n divided by p and n, which is probably familiar to many of you. Now, if you write this alpha, and believe me that this alpha that I presented before can be written in this form, so this is in fact an equality here, then you see that if you have this assumption, then u minus 1 over r minus n divided by pq, so what's in here is positive. Okay, so this is positive. And also this minus 1, which is here, is also positive. So everything is positive here, and you see that then obviously alpha is a positive number, and it is less than 1 because, I mean, this is repeated here and here, so the denominator is larger than the numerator, and this is say a legitimate Holder exponent between 0 and 1, and it's not so hard to believe that this is the sharp exponent if you look at it written in this way. Now, about the sharpness of it, I mean, if you project into the linear case, if you put p equals 2, you get exactly the alpha, which is the optimal Holder exponent for the non-homogeneous heat equation. This was known by different methods. And if f is independent of time, you get this alpha, which is also the optimal exponent for the elliptic case. So this is in fact a sharp exponent. And you can play around a little bit with this. You can try changing the values of p, and you see that the exponent is an increasing function of p. So the larger the p, the larger the alpha. And in fact, as p goes to infinity, this goes to 1, indicating that in the case of the infinity Laplacian, you should get Lipschitz regularity, which is of course consistent with what we know for the infinity Laplacian. Okay, the second problem I want to briefly mention has to do with the degenerate phase transitions. So I'm a little bit lost with time. I think I started at half past, right? So I should be concluding.
Right, it's just 27 minutes from when you start.
Perfect. Okay, very good. So this is a joint work with two colleagues, Paolo Baroni from Italy and Tuomo Cusi from Helsinki. And in these two papers that we wrote together, we treat the so-called Stefan problem. So a phase transition when the diffusion is described by the P-Laplace operator. So the equation is written in this form. So instead of having the time derivative of u, which is the temperature, you have the time derivative of a function v, let's call this v here, which is not the temperature, but it's the energy. And this is the right way to formulate the problem. So typically what happens is that, I mean, if you heat unit mass of ice, you see that as you give energy to the system, the temperature goes up, say until it reaches 0, then you continue to heat and the temperature doesn't change for a little while until this amount of energy, let's call it L, this is called the latent heat of the phase transition, is given to the system, and then after that the temperature goes up again, right? So you need to give the system this amount of energy so that this phase transition occurs and you go, say, from ice to water. Now, if you invert this function here, you obtain this maximal monotone graph, and the V that appears there is a choice in this graph, right? So it's a function that equals U there, equals U plus L here, and here is something between 0 and L, right? And this is the right way to formulate the problem. And we were able to show that, I mean, it was known that solutions were continuous with a certain modulus of continuity, but we have improved that, and we've shown that the modulus of continuity is precisely of this form, with this power explicitly computed in terms of P and N, and here we have a log, and compared with the best result in the literature before our paper, we improved it in 3 ways. So this known modulus was due to Di Benedetto and independently to Caffarelli and Evans. These are results from the early 1980s. And we improved this in 3 ways. So first, we extend this to the case of the P Laplacian. So this was known only even for the case of Di Benedetto for P equals 2. We derived an explicit expression for this exponent. So for us, this is no longer some number, but it's exactly this number, P divided by N plus P. And more importantly, we got rid of one iteration of the log here. Okay, so this, we don't know if this is optimal, but it's clearly a very strong improvement with respect to the state of the art. And finally, let me just mention 2 more works involving colleagues from Brazil. The first one is a joint work with Damião Araújo, who is here today, and my former PhD student, Anderson Maia. And we've derived the exact Holder exponent for solutions of the porous medium equation, which is another celebrated degenerate PDE. Here, the degeneracy is not in the gradient, but in the solution itself. And we have obtained an exponent gamma that depends again only on M, the space dimension and the integrability of the right-hand side. The difference with respect to the P Laplacian is that now we don't know what is the optimal exponent for the homogeneous case, which is in fact a very interesting open problem. The main difference between this equation and the P Laplacian is that we cannot add constants to solutions. This is very important. And the optimal regularity class in this case is C, is Holder, not C1 alpha, like in the case of the P Laplacian. And as I said, we do not know the optimal regularity in the homogeneous case. This is a very, very interesting open problem. This is only known for dimension 1. And finally, we also did the same for Trudinger's equation, the equation I talked about at the beginning, and this is a joint work with Nicolau Dil from Rio Grande do Sul, who did a postdoc with me here in Coimbra 2 years ago. And for the non-homogeneous Trudinger equation, so the homogeneous left-hand side that we talked about earlier, we proved the same type of results. So we derived the explicit Holder exponent for the solutions. And again, this is compatible with the other 2 results. So yeah, I think this is a good point to stop. Thank you very much.